Modern infrastructure divides labor. EV batteries store power, solar arrays generate it. This creates bottlenecks. An EV's heavy metal housing protects cells but doesn't propel the car, capping efficiency. Meanwhile, fluctuating solar output fails to meet constant demand. Neither provides a steady baseload alone. Containers for energy. The future requires embedding power generation and storage directly into the structural and environmental substrates of our world. This roadmap comes from the World Economic Forum's 2025 report on emerging technologies. It identifies breakthroughs that are currently moving from laboratory research into the physical world. To understand this shift, we will deconstruct two specific breakthroughs: structural battery composites and osmotic power. We will evaluate these through the STEEP framework: social, technological, economic, environmental, and policy readiness. A lab achievement is irrelevant if it cannot cross these ecosystem readiness vectors. Mapping the 2025 horizon requires a dual lens: proving the physics and identifying real-world bottlenecks. Structural battery composites, or SBCs, are materials that integrate load-bearing mechanical components with rechargeable energy storage. In this model, the physical frame of the aircraft is the battery. The material architecture begins with woven carbon fiber. This provides the high tensile strength required for a vehicle's structural integrity. This fiber is layered with a specialized epoxy resin to create a rigid matrix. While supporting mechanical loads, this matrix simultaneously allows ions to flow through the structure, enabling electrochemical storage. While current electric vehicles use their battery packs as a structural element of the chassis, SBCs take this further. They allow external body panels of almost any shape to actively store power. This eliminates the dead weight of traditional battery housings, significantly dropping the overall mass of the vehicle. The yield for the automotive sector is substantial. A 10% reduction in vehicle weight improves fuel efficiency by 6 to 8%. This weight loss has a compounding effect on range. Estimates suggest that removing non-functional battery mass could increase EV range by up to 70%. In aviation, the impact is even more pronounced. Implementing structural composites could improve fuel efficiency by 15% over a 1,500-kilometer flight. These materials create effectively massless energy. By turning passive weight into an active power source, they rewrite the economic limits of modern transport. In stationary energy, we look to the river mouth. Osmotic systems generate electricity by capturing the energy released when fresh water mixes with salt water. This thermodynamic process occurs 24 hours a day. Unlike solar or wind, the salinity gradient provides a steady, non-intermittent baseload of power. One primary extraction method is pressure-retarded osmosis. This system uses a chamber divided into low salinity and high salinity environments. A semi-permeable membrane allows fresh water to move into the saltwater side. As the volume on the saline side increases, intense physical pressure builds within the chamber. This pressure differential is then harnessed to drive a turbine, spinning a generator to produce a constant electrical output. A second mechanism is reverse electrodialysis, or RED, which functions without moving mechanical parts.
Humor. An ion exchange membrane system selectively allows positive cations and negative anions to move toward opposite sides of the chamber. This flow of charged particles directly generates an electrical current, capturing energy directly from the water's chemistry. This technology is already being integrated into urban infrastructure, such as the megaton water system project in Fukuoka, Japan. This facility extracts power from the highly saline brine waste produced by standard desalination plants, transforming an industrial waste stream into a renewable power source. Osmotic power turns geographic features and industrial runoff into closed-loop, non-intermittent power plants. Engineering an elegant physical model is only the first step. To achieve global scale, these technologies must navigate the friction of existing systems. The WEF readiness map for structural battery composites highlights a policy bottleneck. Safety standards must be updated for materials acting as both structural frames and energy stores. Environmentally, challenges remain, as carbon fiber is carbon-intensive and difficult to recycle. Osmotic power faces constraints on the technological and economic axes. Technologically, engineers must solve membrane fouling, where debris clogs systems and degrades performance. Economically, building pilot plants requires massive upfront capital, remaining a significant financial hurdle. Physicists have established the core mechanics. The timeline for global deployment now depends on how quickly policymakers, economists, and regulators can align their systems. The 2025 technology horizon relies on re-architecting existing systems to do more with the mass we already have. We are seeing a shift from discrete components to integrated ones, whether that's turning a car door into its own battery or a desalination waste stream into a baseload generator. In both of these breakthroughs, the hard boundary between the machine and its energy source has been successfully eliminated. To advance modern infrastructure, we must transition from passive, discrete containers to engineering the environment itself.